Okay, in this video, I'm going to continue to cover the section 5.6, the linear, the probability distribution. Okay, so so let's see example 5.26, error propagation. So here's a question. So a semiconductor product consists of three layers. Suppose that the variances in thickness of the first, second, and third layers are 25, 40, and 30 square nanometers, respectively, and the layer thicknesses are independent. So what is the variance of the thickness of the final product? Okay, so and then let x1, so here let x1, x2, and x3 and x be random variables that denote the thickness of the respective layers and the final product. Okay, so then as you can see that the random variable denote the final product can be expressed as the sum of all three random variable of three um, layers, right? X1, x2, x3. So now then, the variance of x going to be, since the what the give me a second. So since the variance of remember that sigma I goes 1 through the, for example, they use p, right? P, and then ai, and then xi. That was a sigma a square, ai square. Just give me a second. This is going to be ai square, okay, and then v of xi. Oh, yeah, I forgot sigma right here. Sigma I goes 1 through the p. Okay, so ai square and the vxi, and the plus 2 times sigma. Okay, I is less than j, and then ai, aj. Okay, the covariance of xi and xj. Okay, but since the problem says that the random variables are independent, right? So here x is in the problems example 5.6. X is denoted by x1 plus x2 plus x3. Oops, here. The variance of x gonna be what? Just 1 square times v of x1 plus 1 square times v of x2 plus 1 square times v of x3. Is it? Okay. So it's just simply just sigma. We don't have to consider that terms because the random variables are independent. So I goes 1 through the 3, and then v of xi. Okay. All right. So the problem says that what? The variance of x1 is 25, and then x2 is 40, and then x3 30, right? So that's going to be 95. Okay. All right. Now, next one. So, okay. Now, let's compute the mean and variance of an average. What that means. So, this is a particular linear function that represents the average random variables with identical means and variances used quite often in the subsequent chapter. So let's see. This is a special case of linear functions. Okay, keep in mind this. So first one, what's the average? Okay, so here, again, right here. So mean, we would want to study mean and variance of an average. Okay, so let's figure out average. Yeah, everybody know about average, right? So x bar, right? We just normally use x upper bar, right? That's gonna be what? 1 over p times sigma I goes 1 through the p and then xi, is it? Okay. And then let's say the expected each, I mean xi denote the random variable. Okay, so we deal with the x1 through xp random variables, and the mean is just defined as like that. Okay, and then expected value of each random variable, let's say mu. Okay, so expected value of each random variable x1 through xp is same as mu. Okay, so for I goes 1 through the p. Okay. All right, then what? Then e of x bar is also mu. Okay, so what that means, that is actually what? Expected value of 1 over p. Okay, the sigma I goes 1 through the p and then xi, right? Okay, so that is equal to, let me write the next page. Okay, next sketch page paper. Then since the what expected what e is satisfied linearity, right? So I'll just take out 1 over p. Okay, and the expected value of sigma, right? I goes 1 through the p and then xi, right? Now that is equal to what? 1 over p and then sigma I goes 1 through the p and the expected value of xi. But what we assume that exi is mu, right? For any I. So we got this 1 over p times sigma I goes 1 through the p and then mu, right? Then what? So sigma mu I goes 1 through p is a p times mu, right? So we got 1 over p times mu, which is mu. So I prove it, right? Okay. So now, then we assume that let xi, okay, I goes 1 through the p, okay, p is independent. Oops, no, this is r independent. Okay, so independent with the v of xi, that's sigma square. Okay, definitely I goes 1 through p. Then a variance of x bar, that's going to be sigma square over p. Okay, so now next one. Why v of x bar is a sigma square over p? Let's see. So v of x bar, that's going to be what? 1 over p square. The v of, oh, sorry, not this one. Yeah, this is v of sigma I goes 1 through the p and then what xi, isn't it? Okay, but what? We assume that xi random variables are independent, so we don't have to consider that covariance term, right? So that's going to be then 1 over p squared, and then just sigma I goes 1 through the p, and then v of xi. Okay, then what? V of xi is what? Sigma, right? So we plug in sigma square, plug in there, we're going to get 1 over p squared times what? P times sigma square, which is what? Sigma square over p. Okay, so I prove it. So now next one. Next one, let's see another useful result concerning linear functions of random variable. That is reproductive property. Okay, that hold for independent and normal random variables. So let's see, this is reproductive property, okay, of the normal distribution. Okay, So let's say x1 through xp are independent. Okay, so we assume that. So let's say x1 through the xp are independent. Okay, and then the normals, they are normal random variables. Okay, so that with exi is mu I. Okay, and vxi is just sigma I square. Okay, so now then what y is a linear combination of these normal random variables. Okay, c0 plus c1 x1, okay, plus through the cp xp. Okay, so I mean what, c0 plus sigma I equals 1 through the p. Okay, the ci xi. Okay, all right. Then y is also a normal random variable. Okay, so x1 through xp are independent normal random variable. Then linear combination of these normal random variables independent. Assume that we assume that these are independent. Okay, so linear combination of these random variable is also normal random variables. That's the reproductive property of normal distribution. Say ey that, I'm sorry, this is the y that is a normal, okay, random variable with what? So let's figure out the mean and variance. Ey is going to be is what? C0, right? Okay, so it's going to be C0 plus C, oops, sigma I goes 1 through the P and then Ci and then mu I. Okay, and then the variance of Y is simply what? I goes 1 through the P and then Ci square and then sigma 1 of sigma I square. Okay, so okay, so yeah, this we use here properties E of ax plus b is equal to a times e of x plus b. Okay, we using that proper linear property, right? So you can figure out this one. Okay. All right, now let's see example 5.27. Give me a second. All right, so okay, so let the random variable x1 and x2 denote the length and width respectively of a manufactured part. Assume that x1 is normal with e of x1 is 2 centimeter and the standard deviation 0.1 centimeter, and the x2 is also normal and the mean is 5 and variance, standard deviation is 0.2. So also assume that x1 and x2 are independent. So determine the probability that the parameter exceeds 14.5. So the parameters uh, can be expressed as the what, 2 times the sum of what, x1 and x2, right? It's because x1 x2 denote the length and width. So 2 times the sum of length and width, that is a parameter. So in example 5.27, so we can say the parameter, okay, y can be expressed as what, 2 times x1 plus 2 times x2, right? Since x1 x2 are normal random variables, and then the problem says that they are independent. Okay, so now you can use what, the reproductive property of normal distribution, right? Okay, so anyway, so let's figure out, I mean, what's the question? Question is to find here the question is to find the probability that y is greater than 14.5, right? Okay, to figure out this, we need to figure out what the mean and variance, standard deviation of y, right? Okay. So actually, since y is what normal random variable, we can transform this one to the standard normal distribution, right? So this is y minus mu y over sigma y greater than, right? That's the z-score, right? This is z-score. The 14.5 minus mu y over sigma y. So we have to figure out mu y and sigma y. Okay. Even even if you try to figure out the probability using calculator, you need to figure out the mu y and sigma y. Okay. So mu y is what? This is the yield, expected value of y. Okay. So by the reproductive property of normal distribution, this is equal to what? 2 times expected value of x1 plus 2 times expected value of x2, right? So that's the what? Second, 4, right? 4 times 4 plus 10, which is 14, right? And then sigma y. Let's find us. Let's find the variance. Okay, this is v of y. That's gonna be what? 2 square times the what? V of x1 plus 2 square times v of x2. Right? So that is equal to. So problem says that standard deviation of x1 is 0.1. So then 0.1 square is going to be the variance of x1, right? So 4 times 0.1 square plus 4 times 0.2 is the standard deviation of x2. So square. Okay, so that's going to be calculating this. You're going to get this 0.2. Okay. So let me calculate. Let's find the probability using calculator. Okay, this is TI-84. So we go to the distribution right there, second button, and then here, and then we use the normal CDF. Okay. So since we want to find the probability that y is greater than 14.5, so 14.5, that's going to be low limit. Okay. The upper is infinity, so 99999. The mu is the what? 14. Okay. The sigma is 0.2. We got 0.006. Second. Second. Yeah. So yeah, variance is 0.2, right? So standard deviation is square root of 0.2, right? Keep in mind this. So yeah, so we using calculator. So lower limit 14.5, and the upper is 9999. The mu is 14.5. Sigma is not 0.2, but square root, right? So give me a second. So right here, square root 0.2. Okay. So we got. Give me a second. Yeah, I just made a mistake. Sorry about that. So mu is 14, not 14.5, right? So mean of dy is 14. And then standard deviation is, yeah, square root of 0.2. Okay, so we got the 0.13. Okay, approximately. Okay, so now next one, we move to the next section. Okay. So there's a 5.7 general functions of random variable. So this is one of the main part in chapter 5. Okay. So let's see. Okay, 5.7. Okay. So general functions. So what are you gonna do? So here, We want to find out, sometimes it's hard to find out the mean and variance of a certain type of the probability distribution. So we're going to use the general functions to find out mean and variance of a the probability distribution that is hard to find out them. Okay, so um, okay, so I'm going to find out general function of a discrete random variable. Okay, general function of discrete random variable. Okay, so first one, we suppose that x is a discrete random variable with PDF of f sub x. Okay, so x is a discrete random variable. Let's say just DISC random variable with a PDF. It should be PMF, right? Fx of x. Okay, all right. And then now next one, we say that let's say y is a function of random discrete random variable x. That's to be a one-to-one function. Okay, and then there exists an inverse function. So this is a one-to-one function. Then definitely there exists inverse function, right? And there exists the inverse function. Let's say x is equal to u of y. So what is u? U is inverse function. Okay, so that's actually f inverse. Okay, so now then third one, then fy of y. Okay, let's find out PMF of y. That's going to be probability that y is equal to y, right? So now this is equal to probability that x is equal to u of y. How come? Because what? Since y is equal to h of x, right? That is an inverse function. Okay, all right. So then y is equal the y is equal to h of x. This is equivalent to what? So what are you going to do? Sorry, this is the h inverse. Sorry, I made a mistake. So now we take an inverse function of h. Then u of y, that's going to be x. I mean, yeah, this is u of h of x. Okay, well, actual x, right? So that's x, right? Okay. So now then, what? It means that what? That means y is equal to h of x is equivalent to what? X is equal to u of y. Okay. So that's why we got this. X is equal to u of y. So actually, what? Y means h of what? X, right? Okay. You see. So since this is equivalent to this, we replace this one by this. Okay. So now then this is equal to, that's gonna be what? Probability that x is u of y is what? We can find out this one by evaluating what? The PMF of x. The evaluation of this PMF at what? X is equal to u of y. Okay. So here we finally express the PMF of y as what? Composite function of what? PMF of f and u of y, which is inverse function of this h. Okay. Let's see example. So example 5.28. Okay. So function of a discrete random variable. Okay. So okay, so let's say x is a geometric random variable. Okay, x be a, it says geometric random variable. Okay, with the PMF fx of x. Okay, that is equal to what? P times, right? 1 minus P, or you can say Q, x minus 1, right? So x goes 1, 2, 3. Okay. So let's find the PDF, the PMF, right? I'm just confused. Y is equal to x squared. Okay. So we can consider x squared as what? H of what? H of x, right? Okay. So now, is this the see, the key point is the reason that we got the that expression for the PMFY, because there was just inverse function of h, right? So and then in order to exist inverse function, h must be 1 to 1. So we have to check that this function x squared is 1 to 1. Okay, this is very important. So is this 1 to 1? This is a quadratic function, right? Actually, quadratic function is not 1 to 1 on the entire domain, negative infinity, infinity. But as you can see that what the look at this here, x just goes 1 and 2 and 3, right? So positive number. So in that domain, this must be what? 1 to 1, right? So the quadratic function is 1 to 1 from 0 to infinity, right? So we apply that. So the what? Y equals x squared is a 1 to 1 function. Okay. So on what? 0 to infinity, right? Does it make sense? The function is invertible. Right. Then what's the inverse function? X is equal to square root y, right? Okay. So that's the what? U of y, right? Okay. So then we find out fy of y. That's going to be what? Probability y is equal to y. This is equal to probability what? X is equal to u of y, which is square root y. Now this is equal to fx of what? Square root y. Okay. Now then is what? What's the definition of PMF fx? This one, right? So then we plug in what? I mean, we just substitute square root y into x. Okay. So we got p times 1 minus p to the square y minus 1. Okay. And then y going to be what? What? Y going to be 1, you know, 1 and 2 square and 3 square, because see y equals x squared. So y equals 1, 2 squared, 3 squared, 4 squared. Okay. So next one. So now next one, see, let's figure out the general function of a continuous random variable. So now, give me a second. So now, okay. So now let's figure out the general function of the what continuous random variable. Okay. So oh, see. Okay. General function of continuous random variable. So suppose that x is continuous random variable, and then f of x is PDF. Okay. So let's just say x is a continuous, okay, random variable with PDF fx x. Okay. Now second one, yeah. So pretty much same as the what general function of discrete random variable. So y is equal to, we define y as a function of x. Okay, let's say this is one-to-one. Okay, one-to-one function. Then there exists the inverse function. Okay, so then, so that what? There exists the inverse function of h. X is equal to u of y. So u, this one is what? U is actually what? H inverse. Okay. So now next one, third one. So fy of y, that is equal to, this is the what? PDF of y, right? So this is equal to fx, okay, of u of y times the absolute value of j. So here, the capital letter J is Jacobian. Okay, so that is the absolute value of Jacobian. You may heard this one in calculus 3. But let me explain this. So where what Jacobian is u prime of y. Okay, I mean, so if with one variable y, so Jacobian is just the derivative of u. But 2D, we're gonna get the Jacobian matrix, but that's too much. So yeah, just I'm not gonna explain about that. Okay, so that is called the Jacobian. Okay, that is the Jacobian. Okay, so if you are interested about this one, I mean, if you are curious about this one, what Jacobian, so you can search. You can search, okay, or just search in the textbook calculus. Okay, calculus book. So now, next one. See, give me a second. Mm, yep. Okay. So how come? Why the fy is like this? Well, we got the absolute value of Jacobian, because in discrete random variable, so we don't see derivative. You know, we don't see what you don't see derivative of the x here, right? So now let's see figure out that. So first one, let's figure out probability that y is less than or equals a. Okay, let me start with this. So now then, this is equal to probability that x is less than or equals u of a, isn't it? Okay. All right. Understand what I'm saying? Okay. So now then, since think about this, what can I say? Yeah, one of the examples is why y is less than or equals a is nothing but this. Because so you think about this. Normally, the function is one-to-one. That means that function must be monotone increase or monotone decrease. It's monotone increase. Monotone decrease means that the function is increasing, constantly increase on an interval. Okay, constantly decrease on an interval. That is called the monotonic or monotone increase, monotone decrease. So then think about this kind of increase function. So here, okay, x-axis, y-axis. So y is less than or equals a. Let's say here, think about this. Yeah, a is right there. Okay, so y is less than or equals a. Okay, in order to the y value is less than or equals a, then to do that, x must be what? Less than a certain value, right? Okay, so let's say this is a what? H. This is h of x. Okay. then this is going to be what x value right here. A is actually h of x. Okay. All right. And let's say then inverse function of h is u. Okay. Then the x is going to be u of a, right? Does it make sense? If we say the u is inverse function of h, the x can be expressed as u of a. So now, in order to the a y value is less than a, x must be less than what u of a. Does it make sense, right? This is a special case, okay? But let's say it makes sense. Okay. So now then that is equal to integral negative infinity to what? U of a, right? And then fx and then x dx, right? So now we're gonna change variable. Okay. So okay. Yeah, let me use this one. Okay. So now we're gonna change variable of integration from x to y. Okay, by using x is equal to u of y. Okay, so probability that y is less than or equals a, that is equal to integral negative infinity to a. Okay, so now then, okay. So let me see fx u of y, the u prime of y, u prime y dy, isn't it? Okay, why? How come? I just use a u substitution. Okay, this makes sense. Okay. Does it make sense here? Okay. So x is equal to u of y. I use this one. Okay. So we can make substitution the u of y for x. Okay. Then dx gonna be what? U prime of y and the dy, right? Okay. So then what? When to get the a, when the x is what? Give me a second. Oh yeah. Okay. Now, so to get the u of a, then give me a second. A second. Okay, so now here, so we plug in, u prime y. I mean, replace. Sorry, we substitute u prime y dy into dx. Okay, can you see that here, dx? Okay, this one we change this one to u prime y and then dy. Okay, and then we plug in u of y into x. Okay, all right. So now we're gonna figure out the lower limit, upper limit of random variable y, because y is less than or equals a. So limit of low limit must be negative infinity, upper limit must be a, right? Okay, so that's why we got this. Okay, so now here now give me a second. Now we claim that, so this one, okay, that is the PDF of y. Okay, so it's a question kind of. So question. So is this the PDF of y? Okay. Yeah, so yes, the answer is yes. Why? Because I'm gonna prove it. The first one, in order to that, this is a PDF, a probability distribution function. This it should satisfy what? It must satisfy three property, right? So first one, fx, I mean the u of y, okay, and then absolute value of Jacobian, okay. This one must be greater than or equal to 0. Well, it makes sense. Why? Because the fx is already what PDF. So this is greater than or equal to 0. And then this is absolute value. Absolute value must be greater than or equal to 0, right? So it's trivial. Okay. So this is for any y. Okay. because this is a PDF, okay, the positive, and the answer value is positive, not negative, right? So this is that must be true. The second one, so we have to show the negative what the infinity to infinity, negative infinity to infinity, and then what fx u of y, absolute value u prime y, and then dy must be equal to 1, right? We have to show that. Okay, so yeah, let me show this. Okay, so now then, first one. Okay, so give me a second. We're gonna use the integral with respect to x. Okay, fx x dx. We show that this is we got this one. Remember that we got this one. Can you see? We got that inequality integral by changing a variable from x to y, right? So that integral must be equal to this, right? Okay, right. So then here this is equal to negative infinity to a, right? Fx and the u of y and the u prime y and the dy. Okay. So now then, negative infinity to infinity, fx of x dx, that must be equal to what? Negative infinity to infinity, right? So and then fx and then u of y and then u absolute value, okay, u prime y, okay, u prime y and dy. Okay. So since what fx is a PDF, right? Already this is PDF, okay? So we assume that this is PDF, so this must be 1, so that must be equal to 1. Here's one more question. So right there, when you convert the what? When you just change variable x to y right there, so we got this one here, but there is no absolute value, right? So how we got the absolute value right here? Absolute value. This question, right? So actually we shouldn't put the absolute value, but actually u prime y is greater than or equals 0. So absolute value u prime is nothing but just u prime. I'll show you because what the give me a second. Give me a second. Okay, back to the right right there. So y is okay right here. Just back to this figure right there. So give me a second. So let's take a look at this. So here we assume that the what y equals h of x. This is increase function. The inverse function is also increase function. Okay. So for example, let's say h of x. Wait, yeah, I drew the example. I drew the graph of h of x as example. So just drawing it one more time. Okay. And then inverse function must be this, right? Still increasing, right? So this is h of x. y is equal to h of x. The inverse function, let's say what x is equal to u of y. It's complicated. So I'll really be confused, but yeah, listen carefully. So if the function is increasing function, I mean one-to-one function is increasing function, then the inverse function is also what increasing function. Keep in mind this. So the now right here, then what? If function is increasing, then what? Derivative is positive because that is called the increasing decreasing test in calculus one, right? So using this one, we can say that what u prime of y is greater than y equals 0. Okay. So what if a y of y equals h of x is decreasing? Then also using the similar strategy, we can show that um, you have to put the absolute value. Okay, but let me skip that part. So now then so we show that what? So fy, I mean fx, I mean fy of y is equal to fx and the u of y, okay, times u prime of y, right? Yeah, or you can say Jacobian, but anyway. So we can say this is a PDF, okay? So, and then see next time we'll see example of this, okay? And then we're gonna example of this one, and then we see a moment generated function. So that's the uh, moment generated function. That's the function what we need to find out the expected value and the variance of certain probability distribution function. Okay, that's for today.